welcome to the CERIAS seminar for January 24th. I'm honored today to be able to welcome Dr. Sanjay Madria, who is the Curator's Distinguished Professor at the Missouri University of Science and Technology. Sanjay has been faculty at Missouri S&T since, well, before it was Missouri S&T, used to be known as University of Missouri-Rolla. Got his PhD at the university, or the IIT in Delhi. Has actually spent time on the faculty here at Purdue as a visiting professor. So we are actually welcoming him back to Purdue. He has an extensive record of research in network security, and particularly recently a lot in using machine learning techniques and big data to address cloud, mobile, and network security issues. So with that, I will turn it over to
Thanks, Chris. It's nice seeing you again. I think we met in NSF, I guess.
Yes.
Last time, yes. Thank you. Thanks all for coming, and thanks to CERIAS for inviting me here. I started my career in US here in Purdue, and I remember receiving $50,000 also, a grant in '99. So it's nice to give a talk now. So this talk is based on my paper last year in SRDS 2018, and this research is funded by Air Force Research Lab out of Rome, New York. I'm actually on sabbatical this year, so I'm spending some time there also. So the work basically is focused on, in military and battlefield, and also in a disaster-prone areas. The most important thing is how to get the message in a timely manner, and also we'd like to send the message in a secure fashion. Okay. So as you can see, problem statement that we are talking about the applications of battlefield or disaster-affected area, where multiple groups, for example, in a battlefield, there are NATO forces, so they come from many different countries. And in the disaster, there's a Red Cross, and then there's a FEMA, and then there's all other agencies trying to collaborate with each other. So they need to transfer messages, and also in this case, we are talking about transferring the message in a secure fashion, and also in an efficient way. That basically means we are talking about mobile devices and wireless networks. So the energy and the bandwidth is the most important thing. And if you're a graduate student, I always tell my graduate students that the problem statement has to be very crisp and clear. You cannot describe your problem in 10 minutes. It should take 1 minute, right? So that's why I have a very brief problem statement. So within this, what I'm trying to address is, so what are the issues in that environment? So for example, no infrastructure, so we are not talking about any backbone, for example. So secure message then have to be sent under a store forward paradigm in a delay tolerant networks. How many of you know about DTN? Nobody? Okay, so the DTN is called delay tolerant network. So this is like, what you do is, if you want to transfer a message, you have your phone device or smart device, and then you get the message as you move around from somebody. So you don't know whom you are going to meet, right? And that's why it's called delay. So you do store forward, right? So you store for some time, and then forward if you meet somebody who has interest in that packet, right? So it's like campus, all the students may not be interested in everything. But then the idea is you would like to route the message to some building, and you don't know who is going to go there. And there are many different applications, like people try to using the social aspect, right? So if you're trying to transfer some files about movies, genre, and those things important. So actually, DTN is really used in battlefield and disaster. And there's one very important application I found. In Kenya and other countries where they don't have the bandwidth available, so what the lecturer or the teacher is doing from home, the person downloads all the important lessons on his device and then come to the school, and then based on the topic they distribute automatically to different people. I recently had so this part of a very big project. I'm just doing one part of it, and the whole idea was how you can transfer in a battlefield. Okay, so there are multiple groups are operational, as I said. So the major issue here is finding a node's public key is not always. So we call it always like public key, that we assume, right? In other cases, it's a public, it's available, but not in these scenarios. Okay, and not everybody actually is authorized to even send the messages. So it's not always possible, and only some nodes basically can have authorization who basically can encrypt and forward the messages. So there's no centralized trusted authority or who can generate the keys, for example, or that maybe have been compromised. Even if it's on a Humvee, let's say that Humvee might have been compromised. Same thing, so you cannot do the traditional public-private key thing. Okay, so as you can see, the challenge is how you can pass the messages securely and ensure that they are readable only by the destination node where it is intended to go. And the other challenge is how each node can take care of its own keys and generating the keys and doing the validation. Okay. So what's the contribution here? In this work, we design a secure data dissemination algorithm based on data and key fragmentation. So what we are trying to do first is we are fragmenting the data as well as we are fragmenting the keys. Okay, and then I will tell you how we are doing that. We also support integrity check for both the key and data fragments, because somebody can tamper, right? Or somebody can also drop, right? A simple black hole attack that somebody is not forwarding, okay? And they can tamper either key or they can tamper, for example, the data fragments. So we have done both the things here. What I mean is we have simulated using the DTN simulator called ONE, and we also have implemented this on Android platform. Okay, and I'll show you some screenshots. So some related work. So if you work in security, you might be thinking that possibly you can do using the identities, right? So you can use IBC, but the problem is, again, in the environment which we are talking, it's very hard to know the identities of other people, right? And also that means if you know the identities, then there's a privacy problem, right? Similarly, if you are trying to use attribute-based encryption here, that's again a problem, because we are not talking about attributes here. We are talking about that how these different authorities can basically maintain the keys. So here we are not talking like attributes which are managed by different authorities, right? Here we are talking about the nodes themselves. See, so the one other work which is very close to this is called multi-party encryption, and I have compared my work with this one, and as you can see here that this particular work has this two things called chaining and fragmentation, and they try to address these issues. Okay. So let me explain you how PME works. Okay, I'm sorry this pointer will not work on this side, so I have to only focus here. So let's see here that I have an Alice, and he does not have the public key of Bob, and he would like to communicate with Bob. Okay, and then as you can see, there's an Aaron who does not have the public key of Bob, but he has a public key of Frank. Okay, and Chuck has a public key of Bob, David has a public key of Bob, and Frank has a public key of Bob. Okay, so now the Alice basically has a key and the data. What Alice is doing is it's dividing the key into different fragments, okay, using some algorithm, and I'll tell you what we are using. K1, K2, K3, and then it encrypts the data with the key K. Okay, and this person now basically is going to send this information. Now each one of these nodes is a delay tolerant node, okay, in the network. So they are like going around and getting the information from others. So what this guy is going to do, he meets Erin, encrypts with the public key of Erin because he has the public key of Erin, and send the one fragment K3 and send the data. Same thing, encrypt, send the K1, send the K2. And now Erin is going to do the same thing because he has the public key of Frank, so it encrypts and send the data. Okay? And then Bob basically is going to get all the three fragments and he's going to get the data so he can decrypt. Okay? So the other preliminaries required, how many of you have heard about this recursive secret sharing? None? Okay, so it's a famous Shamir's algorithm, and in Shamir's algorithm what basically happens, you can use one secret and then you can have n number of shares, and then if you get k out of n shares then you can get the key. Okay, that's a famous Shamir's secret algorithm. What I'm using here is something called recursive secret sharing. So what is the difference here? You can basically hide k minus 1 secrets, not just one. So as you can see here that in RSS, k minus 1 secrets are used to generate a k minus degree polynomial, and at each iteration you can hide one secret. Okay? So what happens in that case, that you have a k minus degree polynomial which generate n number of key shares, from where you need only k out of n to generate your key, and then once you have the key you can decrypt. At least k shares are needed. That basically means if any malicious node has k minus 1 share, it cannot get the key. Okay? So that's one preliminary. Then another one is called the Reed-Solomon code, and this we are using basically to generate redundant fragments. Now why we are generating redundant fragments? Because it's a delay tolerant networks. We don't know which node are going to meet, when they're going to meet. The nodes, the packets may be dropped. So what you're doing basically is you are doing the fragments, and then again you would like to have k out of n kind of property for the data. That was for the key. So again, as you can see here, I have the data fragments, k fragments for the data, and we are using the Reed-Solomon code to create additional m fragments using the Cauchy matrix. And here, as you can see, now I have kd plus m fragments using Cauchy matrix, kd fragments, so total of kd plus m fragments, and any k of small d. So small d is not same as the capital D, right? So some number of fragments is needed, which should be less than, of course, kd plus m, right, to generate the data. So what? Here is an example. So you see that I have 4 fragments d1, d2, d3, d4 from the data, and then CRS creates 2 additional fragments d5 and d6, and out of this only 4 fragments are needed to regenerate my data. Okay? So let me give you the overview of the scheme. Okay? So as you can see here, I have a source node, again a DTN node, and it generates a key k, and it has some secrets which it has generated h1 and h2. Okay? So as you can see here, I have a data and I'm encrypting the data with key k. Now what you see here is I have generated 8 key fragments in this example, and I'm using my RSS to generate those fragments. So I have 8 key shares, and then I'm using here the Reed-Solomon code to generate the data fragments. Okay? So in this example, I'm just showing again that I have 4 data blocks, 4 fragments, and then I encrypt this, of course, with the public key of the intermediate nodes. Those intermediate nodes whose public key I have access to. Okay? And then what I'm going to do is just disseminate those key fragments, through multiple paths. Here again I have 6 fragments of the data, and then as you see, randomly I'm just relaying all this data, randomly I'm relaying this data, and all this will go through DTN nodes in an opportunistic fashion, right? Opportunistic, as I meet somebody, I'm going to transfer the information. Hopefully, that node will meet some other nodes and will be able to send the information through some other nodes to the destination. Okay. So, as you can see that I have just written the same thing what I have described, that we use our algorithms. That's why I described the Cauchy matrix. Now, how to handle the key shares. Okay. So, if the destination node's public key is not available, then a node, as I said, has to select an intermediate node. So, if you see here again Alice, and I have a key, I create 3 different shares, and now what you see here, you see that the question is how the intermediate node knows, right? Because it's not going to decrypt. I don't want that node to decrypt anything. So, here what we are doing, again, I don't know if you know proxy encryption. So, the proxy encryption key has a very good function. What it does, it can change the domain of encryption from A to B without decrypting, right? So, it's a key which you apply on that already encrypted, it will just change the domain without decrypting, right? So, you can keep the privacy of the data. So, if you see here now, you see I have encryption, and you see that pre is my proxy encryption key which says A to E. What it means, if I apply this function, right, or this key, it will take the domain of encryption from Alice. A is for Alice and E is for Erin. Okay. So, if you see here, I am sending the K3 encrypted with this proxy encryption function, and E is for Erin. So, this basically will change the encryption from A's domain to E's domain, okay, Erin's domain. And same thing here, you see that here I am using another proxy encryption key because it is subject to different nodes. So, this is A to D, I am sending the share K2, and again K1. So, what I am doing is when I am sending the shares, I am actually encrypting that, as I said earlier, but the way I am encrypting is using the proxy encryption. Okay. So, now you can see that the Chuck has used the C to B key and sent to Bob, and the David has sent this, and then the Frank will send this. Now, Bob has all the shares it needed, right, and it can reconstruct the key K. Okay. So, now let us see how you can handle the data. Now, there are 2 ways you can do these things. One is where my fragments are static, right. Static means I pre-decide how many fragments. The problem with that is there are pros and cons, but the main problem with that is if the message size is small, if I say 10 fragments, I still have to have 10 fragments even if the size is 100 KB, right. But on the other side, the advantage is that I do not have to regenerate this Cauchy matrix, because if you have the dynamic fragments, you have to do the computation again and again. Okay. So, there are pros and cons for that. So, we have done work with both the variations, as you can see here, the static, so where the Cauchy matrix is fixed number of keys and data fragments, and number of packets increases, especially for small messages. So, that is the downside of it. Okay. And in the dynamic, the Cauchy matrix needs to be generated for every message. Now, we are talking about these mobile devices, right. It is very important that you preserve the energy at these devices. Okay. And the packet number then is proportional to the message size, because we are making it dynamic, right. We see that size is 4 MB, 100 MB, 5 MB, and accordingly we are trying to decide the number of fragments. Okay. There is another issue with the fragments is this is a delay tolerant network, right. So, if you create very less fragment, the reliability will not be very high, because nodes, even not malicious, let us say a node is just standing and not moving, right. That basically means the node may not be able to connect with other nodes, and then it is just holding the packet for some time, and after some time the node will drop those, right, because it is not able to deliver. If you create many fragments, right, saying like flooding, you know the problem with flooding is you are basically doing what? Wasting the energy and the bandwidth, right. So, you have to see what is a good balance when you do this. So, now how you handle different security attacks on this system. So, the first is like man in the middle attack, So here public keys are shared only on direct contacts, right? So then this is not possible. I'm only sharing the public key with others when nodes meet with each other. Packet modification, and I'm going to show that we are doing this integrity check using the Merkle hash tree. And then if there's a black hole, redundant packets are already there, right? So if some nodes are going to drop, we are already doing k out of n, right? You don't need all the fragments. And then semi-honest is trying to learn, from other nodes, the pattern. But since we are doing different fragments via different nodes, it's very hard to learn much. Okay, it's not same packet is going through the same path. Okay, so let's see first, the integrity check, because as I said, the nodes may try to alter, let's say, the data packet. Okay, so now this is again an issue, because if you are doing static, right, the Merkle hash tree is fixed. If you are not doing static, then it's dynamic. Then the Merkle hash tree is dynamic, right? So then you have to do more work. So these are the pros and cons of doing the static versus dynamic. So as you can see, I'm showing you here 8 keys, right? I showed that K1, K2, K3, K8. The whole idea behind this is that you should generate, or the node should generate, the same root, right? And if it is not able to generate the same root, that basically means there is a problem. So when the nodes are sending, remember that I said secrets. So what are those secrets? So there are these parameters which you are sending to the nodes, right? Otherwise, how the nodes will know, right, the information. In this case, for example, what I'm sending is, let's see the example so you can see. So when I'm sending K1, I'm sending H2, I'm sending H34 and H58. Why? Because if I have this, I can generate the root. Okay. Or another example is, so if you see K6, H5, H14, H78, I can generate. So the idea is that how to check the integrity is the node will generate this Merkle hash tree and try to see if they are able to generate the same root. If not, they know that somebody has tampered things. So that's for the keys, right? I only showed K1, K2, those are keys. So the question is how you can check the integrity for the data, right? Those are the key integrity. Now, there are multiple options you can do this, but the problem is what is the most efficient way of doing data fragments, because the data size is bigger than those key fragment size, right? So the best we could find is using the elliptic curve cryptography, because it's very efficient. So each data fragment is signed by the source node and then send the signature by appending it with the data block, right? So when you're sending the data, you also append this information. Source public key is put as a secret while generating the key shares. Remember that. That's why we are using that K-1 recursive secret sharing key to append these kind of information with those secrets. Okay, so we can send 4, 5, 6 secrets along with this information. So as you can see here, that I'm piggybacking the information here, that the information about the source public key is put as a secret while generating those share. Then destination can verify the data fragments after they receive, right, because they have the public key. So that's the integrity check. So that's the integrity check for the data. Then the previous one I showed you the integrity check about the keys, right? So now we have make sure that nobody has tampered things. Now we have done extensive simulations, and if you see in this first set of graphs, so here is this is the theoretical analysis I'm just showing you as a graph. Okay. So what is the theoretical probability that, and in the paper we have derived this. Okay, I'm just showing you just the final kind of result as a graph. So here is the probability, and if you see here that I am considering total nodes 100, and I have the average public key possession is 40%. That basically means 40% of the nodes have the public keys of other nodes. And C 8, 10, 13, 16 is how many nodes have been compromised out of those 100. And then I have the intersection of the nodes which have the public keys, and they are in the set of compromised nodes, and that's my X. And then I have the key. So these are the number of keys. These are the fragments for the keys, and this is the data, and these are the fragments for the data. Okay. So if you see here, C is 8 and X is 4. What it means that 4 nodes out of the nodes which have been compromised. So the probability, if you see, this is the comparison with the MPE, multi-party encryption scheme. So this is the probability, which is 0.6, and this is the max and min. And then you can see also the average and the median. And this is the method which I have just described. For the same set of parameters, you can compare what is the probability of compromised messages. So we have very less probability, and they have like 0.3, we have like 0.05 on average and the median. And then, of course, we have done for this different sets. So this is the graph I've generated out of the theoretical bounds which we have. Okay, just to show you, in terms of the bounds, you may not see those things. Okay. So now the performance evaluation. So we use the simulator, DTN, and we simulate it for 222 hours. And the data sets which we have used is the Hagel Infocom 2006 data sets, which are very popular. Node number, so we have 98 nodes. So these are using the real data set. And then message is 152 JPEG files. So 152 messages, and they're all JPEG images. Okay, and key size is 32 byte random symmetric key. D is the data 512, 1 MB, 2 MB, 4 MB JPEG images, and then the number of keys and the fragments 4 and 8, number of data and the fragments. Each data block size, when we are using to create the blocks of the data, the fragments, is 512, it's fixed, and the public key is the elliptic curve, probably 160-bit key, which is very efficient. So now let's see the message compromise. So here is the compromise percentage. So MPE is the multi-party encryption. This is the static fragments. This is the dynamic fragments. And then we have about 30% less compromised messages. And here is the malicious number of nodes. So we have 5%, 10%, 15, 20, 25% out of that 98 nodes. And of course, we assume here for this one, the file size is 2 MB, and then 50% of the nodes have the public keys, okay, of other nodes. So we do like 35% less compromised messages. Bandwidth consumption, because you are sending these fragments, and then you have to make sure that you don't use and consume a lot of bandwidth, and bandwidth is also related to the energy, right? So here is the 512 KB, 1 MB, 2 MB, and 4 MB, and you see that this is the MPE. And the reason, of course, MPE has more bandwidth because they are sending all the time the complete data. They do fragment the keys, but they don't fragment the data. Okay? So in our case, of course, you see the static and dynamic. There's some difference in terms of using the bandwidth, obviously, because the static, you can have less fragments, and dynamic you decide on the static you have fixed number of fragments, and dynamic you can decide based on the size. Okay, and that's why you see the static is taking more because it's fixed. It doesn't depend on this. But dynamic, you see that it catches up when this file size is more. Okay, so the delay distributions. So as you can see here is a tail distribution. You see that at the end. So this is based on the simulation hours. And here is the MPG average. So this is the static 512. This is the dynamic 512, 1 MB static, 1 MB dynamic, 2 MB static, 2 MB dynamic, 4 MB static, and 5 MB dynamic. And this is the number of files received and at different time. Okay, so this is the hours delay, and this is based on that simulation hours. So if you see here, of course, in the beginning, you see that not many files. Of course, you can see that difference is not much, right? So even we are sending the fragments, and they are sending the delay. So if you compare the average, it's a very close, right? And you see that most of the files received at this time, and then of course there are some which are stuck somewhere, right? So you see that it's a tail distribution. So delay to receive message for varying file size, and the file size variation you can see on the top, same file size I've used. Of course, here the average possession of the public keys are 25% of the nodes. Okay? So this may improve if you increase, for example, to 50%. Okay? But we wanted to see, like only 1/4 of the nodes basically have the public keys. And that basically means other nodes are sending through some intermediate nodes. Okay? Energy. So here is the energy in terms of the RSS, right? Recursive secret sharing, because these security algorithms takes energy, right, to execute their algorithm. CRS, and this is the crypto encryption, and that's the integrity. So again, if you see that this is the multi-party encryption averages, and of course you see that they don't have this green box because they don't have integrity check of anything. Okay, so they don't do integrity check of the keys, they don't do the integrity check of the data. So if you see here the RSS, right, and then this is my CRS, and this is my crypto time, and this is my integrity. So if you see on the all the size, of course there is some increase in the energy, but it kind of here you see that more time in the integrity check is basically that means the Merkle hash tree algorithm. The crypto time is again kind of increases if you increase the file size. Now, important thing is that you see that this is the dynamic and this is static. Okay, and this is static. I think there's a typo here. This should be D. Okay, so this is the static and this is the dynamic. So if you see that CRS, you remember that Cauchy, it has to calculate that matrix, square matrix again, and that's where it has to spend some more time doing that. If it is a static, the time will be very less, okay, the calculations. And of course, this is the logarithmic scale, okay, just to show. Delivery ratio, and again, so you have different file sizes, and what I have done here is I have done the delivery of the keys and the data, and I have just taken the ratio of n by k as 1, the data and the keys, ratio is 2, ratio is 3, and it shows the key delivery and it shows the data delivery, right? So if you see that the delivery ratio is much higher for the keys because you saw that there are more fragments there. The data has less fragments because data size is bigger than the key size is because you want to conserve bandwidth. So 512 KB, if you see here, for n by k is 1 when the ratio is 1. This is the delivery ratio. If you have more fragments, delivery ratio will increase accordingly. And more or less, similar behavior, except that when the file size is very small. Integrity check. So here you can see that I have the correct file received, and you see that with integrity check for a static, with integrity check for the dynamic, without integrity. And so if you see the static and dynamic, so this is the green and this is the blue, and then this is without integrity check for static, and this is without integrity check for dynamic. Okay. So of course you see that the correct file received is highest with the static because of course the number of shares are fixed, and this depends on of course how many nodes are corrupted. So more and more nodes are corrupted, you will get less and less number of files. Okay. And of course, if you don't do the integrity check, you see that you get less number of correct files. Then what we did is after that simulation, since we use in the simulation the real data set, we wanted to see some more stuff, so we made some synthetic data set, okay, so that we have large number of nodes. So in this one, if you see the number of nodes 50, 75, 100, 125. And the total energy used in joules, you can see an average energy per node. Okay. So if you see here, even if you see per node, like when the nodes are less, they are spending more energy because they are doing, for example, more data fragments forwarding, also more key forwarding, right? If there are more number of nodes, that may be distributed. Also, if you see again, like hop count, let me just show here. So hop count when it increases, right? What it means that more and more nodes are getting in touch with each other. So the received messages per 7 hours increases, right? So you see that in the first 0th hour it's not, but then you have 80, 47. But when the hop counts are less, you see that they are more distributed, right? And with 125 is the same. When hop count, basically again it shows that how many contacts people are making with others. You see that 110 messages or 99 messages when hop count increases. It doubles, right? So here is the delay distribution, and Cn is the compromised nodes, percentage 5, 15, and 25. And then you have the average collected public keys, 23, 33, 50, and for 25, 33, 50. And then you see here the compromise when there are 50 nodes, compromise when there are 100% nodes, the 100 nodes. So this shows that, what is the delay distribution. So if you see here that 5.8, 5.5, 2.3, and when you have the Cn, which is the compromised nodes, increases, the delay increases, right? Okay. So in conclusion, but I'll talk about implementation after this. So in conclusion, the idea behind this work was that how efficiently you can send the data to other nodes using delay tolerant networks. We want to send the data in a secure fashion, and at the same time we have to make sure that since it's a delay tolerant networks, the energy and bandwidth, they are two more important things. We have to make sure that they are not overused. Okay. We use the recursive secret sharing and Cauchy, Red Solomon, and also proxy encryption and elliptic curve. So 4 different algorithm combination, and then we showed that it's a significant improvement over the MPE scheme. And of course, if there are more compromised nodes, it can do better. Okay, so after this, we implemented all those algorithms in a module. How much time I have?
10 minutes.
Okay, so I should be able to do that. Okay, so we implemented using the smartphones on Android platform using Google Nearby Connections API, which basically make use of the best of Wi-Fi or Bluetooth connection automatically. And each device acts as a node in a delay tolerant network. And at a source, we do the key and data fragmentation, and then target node will try to receive this original message. So here the modules which we have implemented, if you see here that we have a key generator, we generate the keys at each node using the elliptic curve cryptography. We have a key handler, we have data handler, we have key integrity checker, we have data integrity checker. Okay, and then of course on the same side, then you transfer the public keys when they meet each other, share subkeys, messages when they are sent, and share the data fragments when they meet with each other. Okay, so these are the modules which we have implemented in this phone. And of course, this just tells you the flow chart of how you do the communication. So start Google Nearby, connect to nearby device, and exchange the devices. So I have done this work, this kind of system I built for Air Force earlier also, not for this particular work. So we have, all these things experimented with many different technology for communication using the radio networks for the military, Bluetooth, Google Nearby, and so we are just using our previous work for making these connections, and we have tested actually in a it's not the real battlefield, but it's a testing site, Stockbridge in New York. It's on the top of the hill, so there no problem in the communication and things like that. There's no interference. I don't even get my AT&T connection there, for example. So we took all these devices there with soldiers on the go-kart, and they're driving and things like that. And then they have this radio. We try to forward things and blah, blah, blah. Okay. So we have done that work. So here you can see my screenshots. So I have a device, I have a camera, take the image. Is it an on message? So you are the source, or you are an intermediary. And then you have nearby operation, enable, disable for connection. So that's the home screen. Now you can choose either you would like to do the static fragmentation, or you would like to see the dynamic. Actually, I forgot to tell you that we also have priority based, because in case of mission, sometimes we do the priority based. Okay, so you can see that. And then once you click this, so this is the image of my lab actually, this one. So the student sits here, he just taken a wall picture to see that. So this is the create key plus data share. And then the next one, it creates the fragments, it assigns some ID, so this is the type data, message ID, and then share ID, then how many fragments, whether sent, not sent, and things like that. Okay, so you can see those things. And then here, when it comes to proxy, the intermediate nodes have choose a node using its public key, so that proxy key will be generated at the source. So everything we are doing, as I said, at the node level. And then destination message, so you can see that again in the lab he has done the fragmentation and generated different file names. This is just, it's not a really demo, my student, I don't have, in the lab we basically give a demo with 5 phones, and that's what he has done. That is a source and this is a demo, and these are the intermediate nodes, and here is the compromised node. And you can see that D already has, for example, let's assume K1, K2, 3 already received earlier, and D1, D2, D3. And if I2 meets first, then it uses the public key of this, send this, and then it has the PK of the primary public key, and then you send the key to CN. And if it's compromised, then it has to wait for the information from here to complete the fragments. Okay. It's more fun to see when you use the devices than this flow chart. It just shows a one case. Okay. So forget this. Okay, questions?
Yeah, I have one.
Yeah.
The integrity, I'm thinking a very inexpensive way to kind of do an end-to-end integrity check would be to simply do a checksum on the reconstructed data file.
Right, but the problem is I don't want to waste my bandwidth to wait for the end. If the node, the intermediate node identified drops. So that was the main thing.
Yeah, I guess my question on this, yes, there's a cost there, but it looked like your integrity checks in terms of the power required were pretty expensive. Looking at the
we have that energy.
Right.
Yeah.
And it seemed to be pretty expensive. It's up there at the top of that log scale, so once you expand that out, it looked pretty big. I'm wondering at what level of malicious nodes does that, is it better to go ahead and send the potentially bad packets and make a cheap check at the end rather than make the expensive check? There's a trade-off there somewhere.
There's a trade-off.
Do you have any idea where that would be?
No. So what basically the thing is that we want to stop, I know what you're saying, to stop if the node detects that integrity check, because if you let it go, then it may use multiple nodes bandwidth, because you don't know how many hops it's going to take before it reaches, and it's an opportunistic. So we don't want to create so many copies. If we already have fragments, we already have copies. And then now that one fragment is bad, and you let it go. So that's right. So it's a question that whether you let it go, then how much bandwidth it consumes extra, and how many nodes have been, how many messages have been compromised, and so we have not done that comparison. The idea was just stop it at every node, because every node can do that, or the intermediate node.
It seems like something that could probably be estimated analytically. What's the probability that, what's your expected cost of forwarding a bad packet versus your known cost of doing the integrity checks, and your cost of doing the integrity checks for good packets. And I'm wondering, it may be that the answer is a very small percentage of malicious nodes, you're better off doing it this way, but
right, it's possible.
Might be an interesting follow-on.
Right, because what happens, you remember that the fragments we are choosing, I can choose more fragments and less fragments, so it has an impact on that
there's
also.
So many variables that this would play into.
Exactly. Thanks. Any other question? So the follow-on work we are doing on this, not that part of it, but so we are looking into, for example, the images could be similar, because coming from multiple people, and it's like taking the same image. So how to reduce that? So I don't want to do image processing and those stuff. It's expensive on the phone. So we could do that in a very different way. One other work within that is, when people request, we are sending right now the same image, but we are trying to use machine learning and trying to see what is the mission of those nodes and which fragments they may be interested in. Right now, my fragment is like chopping a chicken, I don't see any semantic. And I'm just saying, when I'm saying 4, 6, it's not based on the objects there, right? It's just cutting it off. So now I'm looking into more semantics before doing the fragments. And then all my keys and everything will be then based on the semantics, so that nodes can check, if the keys, and don't forward it if the mission is different and things like that. We are still working on it.
That's interesting. For the image application, I know there are ways of partitioning images such that getting a small number of partitions gives you a low resolution image. Getting a larger number gives you higher resolution. That would be a really natural application for that work. Very interesting. Well, I'd like to thank Dr. Madria.
Thank you for coming.